Okay, first of all, before we get into today's topics, in previous weeks, so we covered arithmetics, print inputs, basic variables and data types. We covered if else. We covered while loops and for loops. Okay, Alisher, like that, right? Uh, okay,
Yeah,
so
right.
yeah, okay. So we covered loops, we covered conditionals, we covered data types and variables, and we covered some functions. Are there any questions about previous week's content or homework or anything?
No.
No, I don't.
Okay. In that case, today we'll be covering mostly classes, which bring us into object-oriented programming, which is again just another stepping stone of a useful tool that we need in order to be able to contribute to real projects. Because to just very briefly summarize why classes matter and what they are, everything that we wrote so far was contained in one file, and it was just either a bunch of lines of code, or at best, with the introduction of functions, we could unite those lines of code. And we could call one function that would execute multiple things at the same time. Not same time, but like in sequence. But thing is, sometimes we have need for even higher level of connection, such as, for instance, suppose that we want to model a brain area, and this brain area must have both its own data and also its own functions that can be called on this data. For this kind of, because let's say this is an object that can do things and that has some data as well. Like for instance, if we are modeling just one neuron, maybe we want to know what's the action potential build up inside it, and we maybe also want to know what other neurons it connects to, what synapses it forms, and maybe want to be able to call spike on it so that it can shoot out the signal and give it to other neurons, which will then maybe also shoot out, or maybe they will be inhibited, so they will shoot out less, and something like that. And so for things like that, when we want to have an object that has both some kind of its own data and also its own functions, that's where classes come in. We'll go through the examples now. And yeah, basically, if you get any questions, as always, just either ask directly or write in chat. Both are fine. And yeah, I'll start sharing my screen now. All right. You see my screen?
Yeah.
Okay. Okay, good. So let's just very briefly remember the things we had last week, which were functions, which execute a bunch of lines of code and maybe return a result, maybe don't. They can take a bunch of numbers of input in them. They can do things, they can print to the screen, or they can just return something, or they can even do nothing. Like this one does nothing at all. It says pass, which just is a placeholder for when we want to do nothing. And this is basically it for functions, and we had just some more complicated examples of what we could do with them. Yes, Alicia?
So I want to ask you
Mhm.
for something. So can you send this file after ending of this
Yeah.
course? All
All
these
of
files.
these examples of functions are on Google Drive. You have a link to our Google Drive, right, from Discord? Let me just.
Okay, but in the Google Drive, I found only uh homeworks.
Uh, Find a folder. There's a folder called Week 4 Code Examples. Let me just link it again, just in case. Uh, one moment.
I got it. Yes.
This one. Yeah, so this one has all of those.
Yeah.
And
Thank you.
whatever we write here, I will also upload. In fact, for previous weeks too, to not have them scattered in a Discord chat, yeah, I'll upload the previous ones as well to Google Drive. Yeah. And
Okay.
yeah,
Thank you.
yeah,
I'll
thank.
wait.
Okay. Thanks for asking, as there might also be some other students who maybe don't know about that or don't know how to access that, so you might be helping them too. So yeah. Okay, yeah, so we had a bunch of examples of what we can do with functions. I won't go through them again, but just main idea is always that functions are grouping a bunch of lines of code so that then we can call them with just varying what arguments we give them. And this avoids us the headache of having to write all of this every time we want to call a function. And similarly, classes will also group a bunch of both data and code together for basically to avoid repeating the logics and also to have a single point of truth. Single point source of truth just means that if we later want to change something, we would also only change it in one place instead of like 10 places that use them. That will become more clear as we get into examples, but yeah, okay. I'll start with examples, but first, are there any questions from previous week stuff?
No.
Okay. Okay. Let's start with the first example of classes to cover today. And yeah, let's see how it goes. I'm just move it here. Yeah, this should be fine. So, in fact, let me just simplify this completely. Even just remove it. The most basic class can be something like just class simple neuron, we say colon, and then nothing at all here. This would be just a class that doesn't have any values or any functions or anything, so it would be kind of useless. But for now, we can just say it like that. And the reason why classes are useful is because then we can create objects of that type. And here's what that means. So previously, we could create some, let's say, integer numbers. We could create some fractions, like, I don't know, 90 is 1.83. We could create some texts, also strings. Or we could create lists, for instance, right? So, I don't know. And so on. But with classes, we can now also create the objects of that new type. So these classes are, so this is of type int, type float, type string, and type list of strings, right? And now here, what we can do is we can say some x is now simple neuron, just like that. Now this is of type simple neuron. What this will allow us to do is to then treat whatever simple neuron defined as members of X. So let's see what that might mean. For instance, let's say that simple neuron upon creation, to say upon creation, we must say it like this. This is just syntax that Python comes with. Let me just write def init. And here we can say whatever we want the simple neuron to get at creation. Like let's say maybe every simple neuron has an action potential of -70. And maybe they have a type, which is like, let's say there are 3 neuron types of sensory, motor, or interneuron. So sensory neurons are like the ones in our eyes, in our skin, or in our ears, which lets us take input from the outside world. Motor neurons are the neurons that we use to control our muscles, so how we move, how we speak, how we blink. And everything else in between, which is most of the neurons in our brain, is interneurons, which are just neurons that take data from neurons and give it to other neurons. So let's say that maybe we can give the type here, and so that type equals type. And now, whenever we create a neuron, we'll say maybe sensory. Maybe we would also have another neuron, Y, type motor. And now, these two objects each contain these variables. In fact, let me print them to the screen just to see what would happen. I will comment out all of this for now, just to see what this would do. So just directly printing it only gives us this thing. So we know that it's a simple neuron object at and this address. So this address basically just means where on our RAM is this place, is this the whole thing stored. So that's not a very useful thing to look at. But one thing that could be useful is if we directly asked what is his action potential or what is his type. And now we can see more useful things about them. So here we can see that for x, the x dot action potential, because we assigned it here, is equal to -70. And for y dot type is equal to motor, because we gave it here. Now, why is that? What did we do here exactly? We could have also not given any argument and just specified this as some default value. In which case, of course, we would not give any argument here either. So in a sense, the creation of a class is like calling a function, just a specific kind of function that creates an object of this type. And we call it init because initialize. And basically, when we call this gets called. And self is just the first argument that goes in to clarify that this is an object that we are modifying, which we are giving this variables. And then we can add any other arguments here that we want, like from type that we had a moment before. Now, to see exactly how this happens, let's actually run through this with a debugger. So when we come here, as of this point, the only variables that exist in the world are just this age, height, name, hobbies that I created here, as you can see right here, but nothing else. But now I am on this line, and once I execute it, like that, we come in here. So this is what gets called. And here, we are getting this object called self, which is a new simple neuron object you can see right here. But it doesn't have any variables or values or anything yet. In order to get them, we will call this line. And now it has this variable called action potential equal to -70. And then we call this line. And now we can see that x has a -70 and type of some default value. Similarly, we will now create the y. It will come in here. And as you can see here, the action potential was created and the type was created. And so now we can see that we have these two variables, x and y. X has action potential, and they have same values right now, but they are stored at different places on our RAM. As you can see here, their addresses are a little bit different. Mostly same, but a little bit changed here, based on how many variables they have to get. Yeah. So just like that, we created new kinds of objects that we haven't dealt with before. Everything we dealt with before was ints, floats, strings, or lists, or dictionaries, which were just combinations of these. Well, and also booleans, I guess. Yeah, like true or false statements as well. But now we have new kinds of things which are neither of those. Now, to better understand them, let's bring back the type. Let's say this is a motor neuron and this is a sensory neuron. Just to clarify what this does. I mean, I'm guessing you might already be guessing how it should work, but just to be clear, here, right after I call this, here you can see type equals motor. So this function is called with self, which is a newly created simple neuron object. And you got supplied this argument, which just says motor. So on line 5, it creates the action potential of -70. And on line 6, it assigns self's type to equal this type. And for this one, it will assign sensory for the same reason. And that is why when we come here, we can see that x is of type motor and y is of type sensory. And we can access these variables by saying x dot action potential or y dot type, and we will simply get the number or the string or whatever is in there. And we can print it, add to it, or do whatever we want with it. So this is the very basic idea of classes. Now let's comment this out and look at a more complicated example. Not too much more complicated, but a little bit more. So far, is it clear what we did? Okay, let me just uncomment this. So far, was this clear?
Yes, it was.
If anyone gets any question, interrupt me at any moment. But yeah, let me just continue. Now let's take a slightly more complicated neuron example. So again, we have a class neuron, and this time it has both init and some other methods as well. By the way, method and function mean basically same things. Method is just function inside the class, and function usually means a function outside the class. So if it's inside, we call it method, but yeah, same thing. Don't worry too much about it. So it has a special function of init, which is again a constructor. Constructor meaning that this is what gets called when we say n equals neuron. So when we try to create an object of type neuron. Here you can see its constructor takes self, which is again expected, nothing, name and threshold. And by the way, as you can see here, we can have default values so that if we don't supply this, that's what it will be assigned to. So right here, as you can see, when we created some n, we said n equals neuron, n1 and threshold equals this. So this n1 became the value of name, and this became the value of, well, threshold. So here we can see that this neuron class makes a name, a threshold, and also spikes, which is an empty list at first. And then this neuron class allows us to call record on it with timestamp, which is just how many seconds have passed, and voltage, just a number, just so we can record our device measurement, for example, in a real world case. And here's what it will do. First of all, this, I remind you, is a multi-line comment. So this is a single line comment. This, on the other hand, is a multi-line comment. So if you see three of these like that, this means that this whole thing is a comment and it also gets ignored. So let me just like that. So what this will do is record the voltage and log a spike if it crosses a threshold. So we record the voltage, and I mean, we don't really do anything with voltage directly, but if it's above some threshold, and threshold just means limit, whatever we set, like in this case, if it's above 0.4, then we will add the time to our list of spikes. Then here we have a function defined called spike count, which just gives the length of this list of spikes. And here we have rep. What rep does is, as you remember previously, when I tried to print the object of type simple neuron directly, the only thing we saw on the screen was basically an address to where it's stored, not the values it contains or anything useful. So by saying def and underscore rep like this, we can change its representation so that if we directly call print n, we will see exact values of it. So to make it clear, let's just comment this out for now, and then I'll comment in back in. So let me just run this code, and everything will become clear. Let's put a breakpoint everywhere, and let's call this. So we come here. At first, we haven't created any variables. We defined this class, but it doesn't have anything yet. So you can see our local variables list is empty. And we want to create n as a type of neuron, and these are the arguments we pass it, right? So because of that, the first step after this is to come here. And here we can see that our name is n1 and our threshold is 0.4, as you can see right here, right? Now, observe the self. It doesn't have any variables yet, but after this line, the name is equal to n1, then threshold is equal to 0.4. We write float here just to make sure that if we were to pass it a whole number, an integer, it will still convert to a float, because that might be relevant later down the line when we want to divide or multiply or something. And for spikes, we create an empty list. And just like that, we can see that in our n, we now have name equal to n1, spikes equal to an empty list, and threshold equal to 0.4. Now, we want on this n object, we want to call the record function. And here's why self matters for this, because that allows us to call this on specifically this object. Here's what that means. I go in here, and we see we were called it with these values. So time s is equal to 0.01, and voltage is equal to 0.2. And just the logic we wanted here is that if voltage is more than our threshold, but as you can see here, the threshold is 0.4, so it's not more, nothing will happen this time. But then this time, we're passing a voltage of 0.6, so it will be more than the threshold. And we will come in here. And here we say that if the voltage is more than the whatever threshold we defined, which was 0.4 as we said here, then we would want to add this time, in this case 0.02, this case right here. We want to add this to our list of spikes. So spikes is just a list we created, which is empty for now. We can see that right here. But after this line, it will not be empty anymore. So now you can see that spikes contains this timestamp. Now we can do this again here, and because 0.5 is more than 0.4, it will again register. And 0.41 is more, so it will again register. So far, we have this variable n, which is an object of type neuron, and it has a name n1, it has threshold 0.4, and it has spikes list of these three numbers. Now, if we wanted to print it directly to the screen, here's what we would get. Let's watch the terminal right here. We get just this is the neuron object at this address, but that's not very useful thing to see. But yeah, spikes count. Here we can see we wanted to know the spike count as well, so we called n.spikeCount, which triggered this method, and this method returns lengths of spikes. So as you recall, len is a function that takes a list and gives you the size of that list. So in our case, the spikes has 3, so we will see spike count is 3. But printing this on the screen is useless, so that is why we define this function called rep, so representation basically, which will give us a string version of what to print when we say print n. And it says that we want to print neuron with name equal to this, and threshold equal to this, and spikes equal to the length of spikes. And so now, if I was to run this code, we would see this is what gets printed, which is a lot more pretty. And to be clear, we could print anything else here. Like we could say just a neuron. And if I were to run this, and just set, we would get just a neuron printed on this line. Or we could go with this more sophisticated way of showing the values of every variable inside it. So just like that, now it will say name equals this, threshold equals that, spikes equals that. So in this sense, this kind of looks like a dictionary. Because if you remember, dictionary also had a bunch of keys, which are just texts, and a bunch of values, which can be a text, a number, a list, or anything. So in that sense, a class is kind of like a dictionary, but you can imagine class is like a dictionary that you can call functions on. So these functions could have been defined outside the class as well, but here's how they would be different. Like, let's go with the example of record. If we didn't have this, then we would not be able to say n.record, but maybe what we could do instead would be to say define record, like let's just create it outside the class. But in that case, instead of self, it would just say maybe some neuron, and like this. And then instead of saying n.record, we would have to say record or n, record or n, and so on. Like this, with this outside, would be equivalent to saying n.record. It's just that when we know that this will always only apply to a neuron, it makes more intuitive sense to put it inside the class so that we know that that's where the logic belongs, just to make code more readable. So technically, you could make all these functions outside the class. This just makes it more readable and more clear that the recording function exists only for classes. And yeah, the first argument is self because this function must be applied to each specific object. Here's what I mean by that. Suppose that we also have another N2 here, another neuron, let's call it N2, whose threshold is a bigger number like 1. If I call this records on N2, they will not be recorded. Like, let me just print N2 as well, and you'll see what I mean. So N2 has a different threshold, and in fact, these ones don't cross that threshold. So because of that, these two won't register as spikes. So if I run this, we'll see that N1 registered one spike, because this one spiked, because remember, 0.6 is more than 0.4. But N2 didn't register any spike. Spikes are 0, because both of these numbers are less than the limit of 1 that we set here. So basically, because they take the argument of self in here, they can be called separately on each object of type neuron. That's the main idea with them. All right, we'll see more examples, so all of this will become more clear in just a second. But for now, are there any questions or anything you would like us to cover again, maybe?
No.
Okay.
No.
Okay, then let's go to a second example. And don't worry, I will upload all of these examples. So here's a second example of exactly what we discussed right before, which is class attributes versus instance attributes. So everything that we write with self dot is going to be unique to each object of this type. Like if you have two neurons, A and B, they can have unique name and unique threshold. But this one right here, species, is going to be same for both of them. Because as you noticed, we said species equals humans, not self dot species equals. Which is why we can say neuron dot species. We can't say neuron dot name because name is not something that is globally shared for every neuron. But species, in this case human, it's going to be same for every neuron in our case. So here, when we create a class neuron, it will have species of human just as a class attribute, meaning that it's for every neuron. And then each specific neuron which will have its own name and threshold. In this case, this one will be a neuron with name A and threshold 0.3, and this will be a neuron with name B and threshold 0.7. And we can see that when I print this, in fact, let me run this. When I run this, you can see here that species for each of them is human, right here. And if I change neuron species, like neuron dot species equals mouse, now both neuron species or A dot species or B dot species will be the same. They will be called mouse. However, we could also create it as a instance variable again by saying A dot species equals custom. And then if we run this again with A species, B species, and neuron species, we can see A species changed, but B species and neuron species remained. So basically, they can have some shared variables. Each specific neuron could still override it just for itself. But the idea is that this will remain the case for neuron class itself. So basically, a class might have its own variables and its own methods, but it cannot have its own attributes that differ neuron by neuron because, yeah, that's the idea. So some both values and functions can be unique to each neuron, and some can be same for everyone. Like for instance, here's a shared methods example. Let's just call it something like shared method example. And this one won't take self. And it will just say, like maybe it will just print, this is a human neuron. And I can call that one without even creating a neuron object. So I can just say neuron.shared method example, and this will call it just fine. But if we want a name or something here, then we would need self his name, saying self.name. And then suddenly I can't really do this anymore. This will give us an error. So for that, I would now have to create a equals neuron with, let's say, name1. I'm just being very lazy. And then I would say a-shared method example. And now it would tell me this is a human neuron with name1. So basically, let me now just bring this back. We can create neurons. I mean, this is just one example. We could be creating dogs or cats or whatever we want to name them, cars, anything. And some things can be unique to each individual instance, like unique to A, unique to B, and some things can be shared among them. That's it. That's the idea. So this neuron.species is same for all of them, but name and threshold are unique to each. Okay, let's rejoin on this call in just a moment when the meeting ends, and we'll continue with our properties. Right now, before the meeting ends, quickly, does anyone have a question?
No.
Now
Okay.
I got it.
Okay, good. Now, right after this, we'll discuss quickly properties, which is basically methods that act like variables. And yeah, we'll just go through everything. Okay, it seems we might have time. Let me see. So these ones, the threshold, spikes, and so on, are variables of any specific neuron. So let's see. Until now, we saw that any simple neuron class that we had some variables, like let me just quickly do this. It had some variables, like let's say self.name is, there you go. That action potential is -70, whatever. And it also had some functions, some also known as methods, which could give us some value. For instance, could return something. Like let's say it could say get, let's say this is first name and last name. And if I ask for full name, let's say the full name from self, I would get return self.first name plus space plus self.last name. Similarly, if I wanted to set name, let's say, for the self, the new first name and the new last name, we would say self.first name equals first name and self.last name equals last name. And so we could say that, for instance, we had some n equal to a simple neuron, and we could print n's. Let's just ask, what is our full name? Our full name is n.fullname, but it's a method, right? So we can't say it like this. We have to say it like this because it's a function. And then we could print full name, of course. And similarly, if you wanted to change our name, we would have to say n.setName, some new first name and a new last name, let's say. Then we could again print n.fullname, for instance. Now, let me just comment this out again. If I run this, we'll see that this will work as expected. So here we'll have a function called full name, which gives us my name, and a function called set name, for which we give the first name and the last name. But properties will allow us to treat this the same as we could treat these. So here's what I mean. If I wanted to get just a first name, I would write n.first name. So I would not have to write this. I would just write it like this. But I can't do that for full name because first name is directly a variable, while full name is actually a function that returns a variable. But if I added a property to it, like this, here's what that would do. Like here, if I add property, now suddenly I don't have to write it like this, I can write it like this. And it will still work. Just here as well. Yeah. Now, this will act as if it was just a variable instead of a function. So the idea of a property tag is to make a function that returns a value, or of course, in that case, it can't take an argument, act as if it was just a variable. So with this, n.fullname and n.firstname are used the exact same way, even though in reality, whenever you call this, you're calling a function that maybe does a ton of computations instead of simply returning a value. That's the idea of a property. Sometimes the reason why you might use them is because maybe you want to keep some things private. So here's what I mean. It could be that maybe, like let's go with the action potentials example. Maybe we don't want this to be directly accessible. For that, we write underscore underscore. And then let's here invent a property, call it action potential self. And this one returns selves this hidden action potential. This way, we would be able to read the value of action potential, but we would not be able to change it. So basically what this allows us is that we can now say print and that action potential. Now, of course, we could have done this without property. In fact, let me do that example right here. We could call it something like get action potential or whatever we want to call it. And we would do the exact same thing. But the difference is, if we went that way, we would have to call this function. So basically, if we don't want to call it and we want it to instead look like a variable, we use the property tag. So these ones actually do the exact same thing. But yeah, by using the property tag, we can make it look like a variable, which can make things more comfortable. That's the idea. So you might encounter some Python code bases that use the property tag, and that's all it is. It just makes a function act like a variable. But this is read-only. You can't say, I can't say action potential equals 5. You can see can't set attribute action potential because this is just a read-only thing. It's just a function that gives us a value. There's no way for us to change the value. This would crash. Now let's go through a more complicated and a more useful example, which actually also includes a way for us to set a value. So here it is. In order to be able to set a value, you also need to be able to get a value. So for instance, in this case, I think we need this line. Yeah, this will work. So let's check what we're doing here. Simply, we have a class neuron. We create it, and we give it some threshold, some number, and we assign to self underscore threshold equals threshold. Underscores are generally meant to be private or protected fields. We'll get into what protected means in just a moment. But the idea is we don't want this to be accessed from the outside. So if you see an underscore at the start of a name, it means that it should not be directly called from the outside, basically. And we also define self, that underscore spikes, to be an empty list. Now here we define a property of threshold, which will allow us to treat threshold as if it was a variable, and actually returns whatever value is in here. And now for this property, we also create a setter. A setter is just a function that will take in a value and will do whatever operation we want. In this case, the operation is that it sets the threshold equal to that value, but only if it's more than 0. If it's less than or equal to 0, it will raise an exception. So this just means that our code will crash in that case. And then here we similarly have made up new property called firing rate hertz. which is just amount of spikes divided by 1. We could have just as well said the amount of spikes, but yeah, let's just go with that. And fire at, we'll just add the amount of spikes. Okay, to clarify what all of this means, let's put some breakpoints in here. Now let's do some experimenting. First of all, suppose we create a neuron. What fields can we access in this neuron? Let's see, print in that threshold. Can we access this? Yes, we can access it. You can see the private fields are not literally inaccessible from the outside. We're just not supposed to access them. But if I call threshold like this, in fact, let me comment this out so it doesn't interrupt our output. If I call in that threshold like this function will be called. So as you can see, let me just run this in debugger. Not sure why that one was called. Oh, it wasn't. It was just my mistake putting the. Okay, anyway. So we have n equal to a neuron, which goes into the constructor and creates our neuron, which we can see right here. It contains a firing rate of 0, threshold of 0.2, and so on. Yeah, everything we defined as a property, we can also see here, even though these are not real variables, they're functions. All right. If I try to print n's threshold, what will happen is this function will be called, and in this case, it just returns whatever this threshold had. That's straight away, right? But if I want to change the threshold to say that threshold equals 3 now, and then print it again, here's what will happen. So first to print it, we return it. And then to set the value, like end threshold equals 3, actually, that is translated into being called on this function. So this threshold function is called with a new value parameter equal to 3, and then whatever is inside here executes. And in this case, we convert it to a float, we check that it's more than 0, and we set the threshold to that value. And then when we want to print it, it comes back. So basically, the property and then threshold.setter, because that's what we called it, together allow us to treat threshold like if it was just a normal variable inside this class, which it's not. To be clear, these are the variables of the class. This is not a variable, this is a property, which means that it's dynamically computed. So it doesn't actually exist until we call it. Is this idea clear?
Yes.
Okay. We will have some
Yeah.
homeworks on this, so yeah, this will be reiterated. But yeah, let's continue for now. Now, another thing is let's define class methods and also static methods. So for both of these, basically the idea is that we have things which, how do I put it? I'm not sure if we can have a good example of this. But okay, so here's a rough idea. We have a class of spike train in this case, for example. Of course, we can call it whatever we want, some nonsense name as well, but let's just stick with something that makes sense. And we have an initializer like before. This is known also as a constructor. constructs an object of this class. And in this case, it just says that times s is some variable of this class. And we convert this to a list and assign it here. So right here, you can see this is lists of 10, 20, and 45, for example. Basically, from ms, now this is what a class method does. So basically, it allows us to take the class type, which we might use to create an object of this class. So here's what this does exactly. Let me just put this everywhere to make it very clear what we are doing here. So roughly, this function will create an object of type spike train and give it the arguments based on this function for each of them. Let's break this down because it's a little complicated. In fact, let me simplify this right here. We'll say seconds. Okay. So this is just a computation of times in milliseconds being converted to times in seconds by dividing them on 1000 because there's 1000 milliseconds in a second. And this is an inline for loop. If you remember from before, this is equivalent to saying for t in times ms, like this is equivalent to saying that seconds is an empty list, and here seconds dot append master ms to s of t. Like this is equivalent to this, just in one line. So we call this on each of them. Basically just means that we got a list of times in milliseconds and we're converting them to a list of times in seconds. And then we are calling this init function with a list of time in seconds. Now, to see that very clearly, let's start from here and everything will be obvious. So we come here and we say spike train from ms, from milliseconds. And this will trigger this one. So let's go in there and see what happened. So the from ms was called with class, which is just spike train, and times ms, which is just the list that we received, 10, 20, and 45. So class being spike train means that we can say class ms2s, which we'll just call spike trains ms2s. It also means that, like, instead of giving this, we could have just said it like this as well. But the value of specifying it like this is that if we later create a child class, and we'll see what child class means in a moment, we'll have more flexibility. But anyway, right now, let's keep moving. So we convert these milliseconds to seconds by saying that we go through each of them, we call it a variable t, and we call this function on each of them. And this is the function we are calling. So for each of them, like for 10, we divide by 1000, then for 20, and then for 45 as well. And so our second data is now a list with these values, just divided by 1000, basically. And then we will create an object of this class. So we are calling this with that second string. So let's see. We come in here, we assign that, and just like that, this st variable now holds a spike train class with these variables. That's the idea. It's a lot of topics that we're covering at the same time. Don't worry if some of it doesn't click instantly. We'll have some homeworks and examples of this. But basically, yeah, just like that, we use the function to create an object of a class instead of directly saying st equals spike train and whatever, and passing some values here. Like instead of this, one way to directly call constructor. But instead of that, we used another way, which is to just, call function, which will create it for us. Now, if we print this to the screen, we go into this represent that we created, which will just say spike train, and then followed by the list. So right here we can see it didn't get printed yet. One moment. Let me see what we did wrong. Oh, yeah, there it is. Anyway, it called and said spike train with these sizes. Then length, which is just length of a spike train. We can redefine how we define lengths for each object. So for a list, the length just means how many objects it has. For a string, length means how many characters it's made of. And for a class that we create, we can define what length means. So length is just another function which will return some number as a value. In this case, we said that our length function will simply return the length of our list times thing that we have. So when we say len on our st, this will return the len of the times thing. And now if we want to convert this back into milliseconds list instead of being seconds list, we can call seconds to milliseconds function that we have right here, which will basically multiply it by 1000, round it to a whole number, and represent it as an integer. And then we do that for each of the values in our list, just like that. And we see that right here. As milliseconds, they are back to 10, 20, 45. So I know this might be confusing, some of the syntax, but it will start to click as we go through more examples and as you go through the homework as well. So don't worry about it. But if you do get any specific questions, feel free to interrupt me at any moment. Feel free to ask and we will discuss it. All right. Do you have any specific questions?
Not for now.
Okay, good. Let's continue then. So now I want to briefly discuss first the idea of composition, and then later we'll discuss inheritance. So composition basically means that we created a class called neuron, right? It has a name, it has a list of spikes. It has a function fire, which adds some timestamp t to our list of spikes, spikes being numbers in this case. And then we can call represent on it, so that when we say print on an object of type neuron, it will say neuron with this name and with these spikes. So we just define neuron like this, just as before. And now we introduce a new element, which is a class called network, for instance, which will use a bunch of neurons. So basically, when you create a class, then you create some new class that will use this class as a variable or in some other form, mostly as a variable. That's called composition because you are composing a complicated object. Like one example of composition would be, imagine if we had a building, some class building, but before that, imagine we had a class called, in fact, let me just write that as code. Suppose that we have a class called wall, which has, I don't know, maybe height of 10. Maybe a class called kitchen, door, with a height of 10 as well, for example, or height of 8. Class window with a width of 4 and height of 2, maybe. And let's say now we have a class floor of width of 10 and length of 8. And now we want to say class home, and inside it, we might say that its parts are just a door, a bunch of walls, like let's say maybe so of that door is a door, so of that floor is a floor, Self.walls could be a list of walls. So like this, maybe 4 walls. And self.windows could be a list of windows. So window, for instance. And just like that, we would have a home that is made of all these different parts. And maybe we could even have then a neighborhood. Let's initialize it as well. That would be made of a bunch of homes. So like self.homes are a list of home, world, and so on. And then we could have a city made of neighborhoods, country made of cities, planet made of countries, galaxy made of planets, whatever. The idea is if we reuse the classes like this, so we define the classes and then we use them inside other classes, and then maybe we use those classes inside other classes and so on. This is composition. Okay, is it clear what composition is?
Yes.
Okay, good. Now back to our neuroscience examples. We have a class of neuron defined like this, and we have a class called network, which in its constructor receives neurons, which is apparently a list, and assigns self that neurons equals list neurons. We could say it directly like this as well, but just in case it's maybe a tuple instead of a list or some other collection, we make sure to convert it to a list. Then it defines a function called broadcast, which gets some list of values to give to each neuron and goes through each neuron and through each value, and it calls the fire function defined right here for each of the neurons. And similarly, it has a function called total spikes, which gives a sum of the lengths of spikes for each neuron. So basically for each neuron, how many spikes they have, and then it gets summed up. These are all examples of composition because, yeah, basically because it has a variable that is a different class that we created. And it could have had any other class, other function as well, like say hi, like we can be very simple here, and hi, or it could have something complicated like this. So all of these are still composition. Anyway, when we come in here, we have N1 and N2, which are neurons that we create. We have some network that we create, and we pass it the N1 and N2. And we can call broadcast on it, and it will put these values in each of these neurons. Then we can print what the values of these neurons are, and we can also print the total spike. So let's see what that will actually give us. So you can see that for neuron 1, we have 3 spikes. For neuron 2, we also have 3 spikes because we passed these 3 to each of them. And the total spikes are 6. So similarly, if we had another spike here, it should get 4, and the total will be 8. So this is the idea with composition, which is basically that we can, use the classes that we create in other classes. All right, I'll send this example as well. I think we have covered this. Let's move on. Now we get to something more new, you could say, something called inheritance. Inheritance is when we want one class to completely contain every field and method and everything from another class. So before we touch this complicated example right here, let me just comment this out and quickly use a simple example. Let's say that there is a class called creature, and in its constructor, suppose it defines a lifespan of how many years this creature can live. Let's say software lifespan equals lifespan. Now let's say that we have animals, a type of creature that can move, right? So their constructor will include also lifespan and like movement speed, let's say move speed. Animals are a kind of creature, so we do it like this. We say this. So here, we must say me see if I'm doing this wrong. Just a moment. Okay. So let's define it like this. Let me remember that for a second. So, oh yeah, super init, right. So we say super init with our lifespan. And then we say self.move speed equals move speed. And similarly, let's say that a type of animal is a bird. And let's say every animal can greet us by default by saying hi, or like some random noise, because animals can speak. But birds, which is a type of animal, let's say, which have lifespan and move speed, also have a greeting. So they will call this animal constructor in them with lifespan and move speed. They will also define their own greeting and store it. And their version of greet will actually say whatever their greeting text is. And let's see how this manifests. So let's say that we create some creatures. Let's say A is just a simple creature with a lifespan of 10, for instance. Let's say B is an animal, not just a creature, with a lifespan of 20 and move speed of 5. Let's say C is a bird with a lifespan of 15, move speed of 10, and a greeting that says, nice to meet you. Bird has everything that an animal has, like let's say in pain. So it's A. So we can call, for instance, C dot in pain, and we can see it will print A, even though this was defined in animal, not in a bird. Because the bird derives from an animal, it contains everything that the animal contains, plus its new things. It also overrides some things that the animal contains if it uses the same name. So you can see that animals say asofo when they greet you, but birds greet you with their own greeting. So if I say b dot greet, which is just an animal, we see asofo printed. But if I also say c dot greet, we'll see nice to meet you, because a bird overrides this function by giving it same name and same arguments and does something else with it. Also, what is this super init? Basically, this means call the constructor of my parent class. So in this case, let's examine exactly what happens when we create just the bird, nothing else. So let me just put this everywhere and we'll see what happens. So when I come here to create a bird, we go into bird's constructor, and the first thing we do is we call its parents, which is super, which just means parent, in this case means animal. We call the parent constructor, and we give it the lifespan and move speed. So we call basically this thing. So we come in here, and in here, before we do anything, we call its parent constructor, in this case creatures. So it goes here. And here we assign the lifespan to 15 that we had, and then we assign the move speed. Then back to the bird, we assign the greeting as well. And now the C object has greeting, a lifespan, and move speed. And we can call the inPain function that it has, for instance, which will go into here, even though this is animals, because bird is also a type of animal, and it will print this R to the screen. This whole thing that we just saw is called inheritance, and it means that if class bird derives from class animal, then bird contains every function and every variable that animal contains. Similarly, without the birds and animals and such, we have a similar example down here, but it expands by also introducing the idea of an abstract method. Abstract method basically means that the parent class doesn't implement something at all, and every child class has to implement it. Like in this case, there's something called read. It's marked as abstract method. For that, we had to import from here, from ABC, import ABC. And this is called abstract class. And that tells us that sensor is not supposed to be created directly. Instead, it's supposed to have a child class, like in this case, sine wave sensor, or random spike sensor, or whatever. And they are supposed to define this method again, and this time with actual value. And then we use it the same way anyway. We run this. And it gives us the values and functions and all that. I want you to dissect this yourself from what I will upload. But yeah, basically the idea with this is that we can have some methods that are not defined at all in a parent class, and the child class has to define them in order to use them. This is called abstract methods. If we use it without defining it, the code will crash. That's the idea. Now, this might be a little overwhelming, but don't worry. And we will need just a few minutes to finish up this lecture. So once this meeting ends, let's rejoin. And in like 5 minutes or so, we will finish our lecture. Let me see what we have left. Yeah, we can speed run this. But basically, this is the main idea. Do you have questions about this kind of inheritance? Like, let's just stick with this simple animal inheritance kind of thing.
No.
Okay. So this was the idea with inheritance, which is that we can have a class, and then we can have a child class which derives from it and takes every function and variable that it had and plus adds its own things. We can also have, as demonstrated here, abstract methods, which means that this function doesn't exist in the parent class, but it forces the child class to create it, basically. And that's it for now. Now let's move on to our other remaining topics. So these are all the special methods that we need to be aware of. So len allows us to define, writing like this, underscore len, allows us to define the lengths of our custom class. So in this case, it allows us to call this len st. Calling this, we'll call this, just like we did on lists and on strings. Similarly, iter allows us to iterate on our class, which basically means that we can put a for loop on it. So previously, we used for loops with ranges and lists, as you recall, like if we had names, we would say for name in names and then print name. And this would just give us these names printed out like that. And then we said that we could also do this for numbers, like let's say for x in 1 for whatever, we could print the x. Right here. Yeah, you can see this right here. And we also said that we could print for range, which is useful for indexes. So for I in the range of 100, for instance, we can print I. And this will give us just all the numbers from 0 to 99 printed out. Now, we can pass a for loop over anything that can tell us what value to have at a time. This is called iteration. So the things that allow this are iterators. And you can say def iter on self and define the logic. Simplest way would be to say return whatever iterator our inner list has. So in this case, our spike train has a list of times. So basically all the operations we do, the length, the iteration, whatever, are really done on this list that we have here. So we will just be calling the iterator of this list and so on. We are also able to define get item, which allows us to do this. So similarly, should have a set item as well, I believe. See if this is true. Yeah, this is true. So we also have get item and set item, which we can use to define what it means to get the ith element of our custom class. So as you recall, in a normal list, like if we had names, again, we could say name set 2 equals no one, or print name set 0. And this would simply give us names like this. But for our custom class, we can similarly define what does it mean to change a value at a specific index, or what does it mean to ask for a value at a given index. So to ask for a value at a given index is really just to call get item with this as argument. And we can have as complicated of a function here as we want. And the set item is similarly is for assigning a value. Like if I want to say names2 equals no one, for our custom class, that would mean calling the set item with I and the value, and then self dot times equals value. So in our case, for our spike train st here, st2 equals -1 right here is the same sentence as if I was to say set item add 2 to -1. So this is the same as this. And similarly, print st1 is same as print st get item 1. Same as above. So they are just what's wrong? Yeah, like that. Like that, I mean, yeah. So as we can see, yeah, these are the same things. Just get out of here now. And what this means is that these are just shortcuts which can tell us some useful things. Like they're basically there to make our syntax simpler, to make our code more understandable and clear. Similarly, we have contains, which is what we use when we ask this in st. So if I want to ask 1 in st, this is the equivalent of saying print st dot contains 1. So these are also equivalent. This is what that means. And rep is just what happens when we write print on the screen. So these are all the special methods that you should be aware of. This is constructor that creates the object. This is length, iteration for loop. Yeah, basically like this. Is this clear?
Yes.
Okay,
Yes.
let's move on. Similarly, just two more things to define quickly is a string, which will give us a string representation. This allows us to, like, rep is specifically for printing to the screen. Str is for converting this whole thing to a string, which we can then use, manipulate, or whatever. Like, they're basically same. It just means that if we write it as a string as well, it will allow us to convert it to a string variable. Like, it will allow me to say x1 as text is str x1 and print x1 as text. And it will print this to the screen. So the idea is that writing string would let you to convert it to a string like this, and then maybe get the first 5 letters or whatever if you wanted to. But if you just want to print the whole thing, rep does the same thing. And one more thing, we can define what it means to be equal. So what it means for two, in this case, this is a class experiment. What does it mean for two objects of class experiment to be equal? We can say def __ egg, this guy with some other. If it's not of type experiment, then we don't care. But otherwise, we say that maybe in our case, name, subject ID, and trials must be equal for both of them. Or we can define it as whatever we want. So basically, if we redefine the equality, then as we can check right here, we can ask something like x1 equal x2, and this will call this function and return true or false. So for example, in Python, lists are equal if they contain the same elements. In some programming languages, they're not, but in Python, they're considered equal as long as they contain the same elements. And similarly, for our custom class, we can define what it means to be equal. Like usually, you might say that if all the variables have the same values, then they are equal. Or maybe depending on your special case, you don't want them to ever be equal, or maybe you want them to be equal if their name is same, regardless of these other fields. So it depends on your use case, but this allows us to basically ask this question: x1 equals x2 and get true or false answer. All right, so that was just another example of special methods. Now let's move on. Data classes basically allow us to do a little bit of a shortcut. So that, like, as you notice here, what we are writing out here is kind of obvious. We are saying class name and then all the variables it has with all the values, which is kind of the default behavior of what you would want. So you might just say, just like this, data class. You can put this tag on any class you want. And now suddenly you can print it to the screen and it will show it like this. So that's the advantage that it gets, basically. You don't have to memorize this, but yeah, this is basically the equivalent of defining rep. Yeah, this is the equivalent, basically. So that you don't have to say like def rep self return session config and whatever. Instead of doing all this, like now it overwrites, but if I remove that, I get it from this data class thing. If I didn't have that, I would just get the address, of course. And just, like if we said like this, of course, we would just get the address and nothing else. But if we have it as a data class, then suddenly we can print it to the screen and we get all the variables and their values. This is the idea with data class. Okay, I am quickly going through this, but you don't really need this unless you go into very specific codes. I just want you to be aware that there might be such tags on top of a class or on top of a function, and they can mean a couple things. So property meant that it acts like a variable, a function. Data class means that you get some useful stuff, such as, for example, that you can print it to the screen and it will print all the variables instead of just the address. Don't worry too much about this, but I will upload it as an example. Okay, let's continue. And yeah, this is just one more thing that we need to be aware of. So sometimes we might have a class that uses some kind of external connections. Like maybe it connects to a database, or it connects to some device, or maybe it opens a file to read it. And we need to be able to make sure that this connection will also be closed. And for that, whenever basically, if we open something, we also need to be able to close it. And Python actually gives us code to make sure that we don't forget to do this. So generally, if we have some class connects to robot arm, maybe we might have some diff connect that does something, and maybe a disconnect as well that does something else. Like let's just print connected, and similarly print disconnected, right? And we might say some controller equals connects to robot arm, and we would call controller that connect, then do some robot movement things, and then controller that disconnect. Let's say, in fact, I will ignore this so that I can walk you through this. So problem is, what happens if either this code crashes or I simply don't remember to write disconnect? In those cases, the connection would remain open, and that might give us some problems. Maybe it would overload the device or overload our computer or something. So to make sure that I don't forget to use disconnect, Python actually allows us to define methods of enter and exit. So here, Python allows us to say there exists a method called enter. I forgot to say self here. Enter, which will pretty much just, in our case, say connect, and exit, which is self, and also these things, which we don't really care about right now. We just need to have them. And in this case, we'll just say disconnect. Basically, these ones will tell us whether we disconnected because of a crash or on our own. But basically, we define how to enter and how to disconnect. And now, instead of having to write connect and disconnect, what I can do is I can just directly say with controller connects robot arm as controller with this syntax, do some robot movement things, and then let's say print done moving the robot, and then it will disconnect. So let's see what that means. So I call this, and it will connect. It will say done moving the robot and disconnect. So just to be clear, ready, and over as well. You can see it comes here. Then as we are about to enter, this is called. And the moment we enter, this enter thing is called, which in our case connects to the robot. And as soon as we are done with it, it disconnects from the robot. So basically, this allows us to make sure that we always close whatever connections we open, such as if we are reading a file, connecting to a database, a robot arm, or whatever it is. So we would say with, give our variable, as, and so on. Python has similar thing for opening files, which is something that we will touch on in the next lecture. But yeah, basically this was just another example of exactly that. So we defined some entering logic and exiting logic, some record event function, whatever. And here we said with recording session, so we created one class of this. We call it ses. We call these functions, and then we disconnect it. So let's see what that would look like. Session started, these things happened, and then session closed. So this is the idea with enter and exit, which allows us to connect and disconnect to whatever we want, or do whatever logic upon connecting or disconnecting that we want. This is important because if we forget to do this, sometimes our memory might grow and grow and grow, and eventually our computer can crash if we have too many connections open because of leaky logic like this. Okay, this is the idea I wanted to explain. We will see more examples of with when we deal with files in our next lecture. But for now, just very briefly, whenever we have an object, we can ask if this object an instance of this class. And this is a question which allows us to then make sure to act differently. Like in this case, let's say that we have class sensor, we have sine wave sensor that is its child, and random spike sensor that is also a sensor's child. We can ask a couple things. One thing we can ask is subclass some child to parent? So is subclass will only return true if this is the case. In this case, of course, it is because sine wave sensor is a subclass of this. And also we can ask use sensor function, let's say, which takes an object, and it will say is instance of this class. So in fact, let's see what it gives us. It says sine wave is indeed a subclass of sensor. It's true. The first object in our case, S1, is a random spike sensor. And the second object is not a sensor at all. It's just some string. So this is false for it, this is false, and it comes all the way here. So basically, is instance allows us to check if a certain object is of a type of certain class. That's the idea. Because maybe we created a lot of classes and we want to know what we are dealing with right now. And just one more thing, try, except, and finally. So we kind of mentioned this before, where we can raise errors which will crash our code. But if we want to crash only part of the code and not the entire code, what we do sometimes is we say try. We put some code that could crash. In this case, we're crashing it on purpose, but maybe it's not on purpose. And then we say except value error. So if this kind of error happens, handle it. And then we say finally, do this. So to see exactly what this does, let me just put this here, and we'll see what we're dealing with in a second. So we come to a neuron, we create a neuron, and let's say we want to call this set threshold function. We come in here, we have a value of 0.8 in this case, right? Which should be fine. So it goes through the try, then it goes through the else, because else happens if it didn't crash. So threshold is assigned. We get this text pointed to the screen, threshold set to 0.8. And we go to the finally part, which says attempted update. Now we do the same with a negative value. In this case, we come in here, v is less than or equal to 0, so we raise a value error, so we crash on purpose. We catch our error, and we print invalid to the screen, and then we go to finally, and we say attempted update. And then in the next case, we take text, which is of course also wrong. We cannot convert to a value, so it crashes. But the crashing error is not of type value error, it's a different kind of error. Actually, it is still a value error, never mind. And yeah, we say attempted update. So basically, this allows us to more intelligently handle the cases where our code crashes. We have try, we have except, we have else, and we have finally. I'll show more example of this in homeworks. And that's okay. That's all the topics that I wanted to cover for today. So it might feel like a lot, but actually it will all click in place after you do a few of the homework examples. So I'll make sure to give a proper homework that reintroduces these concepts in a more clear way. But with that, yeah, we're done with today's lecture. So we covered classes, composition, inheritance, and this try, catch, except finally thing. Do you have any specific questions?
No.
Okay. Then with that, our today's lecture is done. I will upload all these examples to Google Drive and this lecture to YouTube, of course, and I will send the homework soon. We're done with basics of
Thank you.
Python, and next week we'll be actually connecting this Python thing to neuroscience with a brain-computer interface. So I guess next week will be a little more fun. And yeah, with that, I'll see you next week.